Good afternoon, everyone. Today I'll present research on the economic value of climate forecast precision in agricultural markets. This work examines how forecast accuracy influences farmer investment decisions and risk management strategies. Climate forecasts have become increasingly sophisticated in recent decades. But here's the key question. What is the actual economic value of improving forecast precision, and how does this value vary across different types of farmers? Agriculture is one of the most climate-sensitive economic sectors. Production outcomes depend critically on temperature, precipitation, and extreme weather events. Accurate forecasts enable farmers to optimize planting dates, select appropriate crop varieties, and adjust input applications. So let me explain the theoretical framework. We model a farmer who must decide on investment levels before observing the actual climate conditions. The farmer receives a forecast signal with precision theta ranging from 0 to 1. Perfect precision means theta equals 1, while a completely uninformative forecast has theta equal to 0. The farmer maximizes expected utility, considering both returns and risk. More accurate forecasts shift the probability distribution towards states consistent with the signal, altering expected returns and reducing uncertainty. Now, the economic analysis reveals four main value channels. First, productivity improvements. Better forecasts enable optimal matching between production practices and realized climate conditions. Second, risk reduction. Even holding productivity constant, reduced uncertainty benefits risk-averse farmers. Third, resource allocation efficiency. Forecasts help deploy scarce resources when and where they yield highest returns. And fourth, market coordination. Though this one is more complex. Common forecast information can align decisions, but excessive coordination may amplify supply volatility. Here's a critical finding. Forecast precision exhibits diminishing marginal returns. The first improvements in accuracy resolve fundamental uncertainties and generate substantial benefits, but subsequent improvements provide increasingly smaller gains. Now, let's discuss market failures. Climate forecasts have public good characteristics. They're non-rivalrous in consumption, meaning one farmer's use doesn't reduce availability for others. This creates underproduction when forecasts are privately provided because producers cannot capture the full social value. The analysis also reveals important heterogeneity. Large commercial operations with sophisticated systems can extract greater benefits than smallholder farmers. This pattern suggests that forecast improvements alone may exacerbate agricultural inequalities. So what are the policy implications? First, public investment in forecast infrastructure is economically justified. National meteorological services should maintain observational networks and produce basic forecast products. Second, capacity building is essential. Farmers need training in forecast interpretation and strategies for incorporating information into farm planning. And third, dissemination systems must ensure equitable access, particularly for vulnerable populations, including smallholder farmers. In conclusion, improved forecast precision generates substantial economic value through multiple channels. However, realizing these benefits requires coordinated investments in infrastructure, farmer capacity, and complementary services. The economic framework developed here provides a foundation for evaluating forecast investments and designing institutional arrangements that maximize social welfare. Thank you for your attention. I'm happy to answer any questions.